Noise happens when things get really quiet. We start noting this hum and fuzz and hiss when the signal isn't present. But when the signal gets really loud, we have an issue also. As we get really, really loud, as you go through pieces of gear, you're going to find that the gear will start causing distortion. We can also call this the nonlinear range of the piece of equipment. So with our dynamic range, again, is the distance between the noise floor and that distortion. But what actually happens when we hit that point of distortion, that kind of threshold of this distortion, that amplitude at which the device starts acting in a strange way? We find that as we start pushing more and more level into that threshold of distortion, we start getting more and more high end. In fact, we can consider it that volume variations actually turn into timbre variations when going through some kind of distortion stage. And we hear this term gain or drive. And drive is just a gain stage before one of these nonlinear places. And if you talk to a guitar player, they're dealing with drive all the time, right? Electric guitar player will plug into their amplifier and they'll turn up the drive. And the drive is really just a volume control, but it's going purposefully into one of these distortion stages, going purposely into this distortion threshold. And as they turn that drive up, the sound of the guitar changes. It gets brighter and brighter and grittier and grittier. And that can really help a guitar player. It helps that guitar punch through a complex, dense mix. And it also emphasizes the musical dynamics. As a guitar player plays harder and harder and louder, or turns up the volume on their guitar, it's going to get brighter and brighter going through that stage. So that's a great musical usage of distortion, emphasizing musical dynamics and letting that instrument come through in the mix because it gets brighter and brighter. There are many times, though, when we want to avoid distortion. If you're recording a vocalist, say, we want to avoid distortion. We want a clean vocal. Now, when you're recording a vocalist, there are numerous places in your signal flow that it can distort. In fact, every one of those pieces of gear that it can go through is a place that you can get distortion. The microphone itself can distort. If you have the mic too close to the singer's mouth, it can possibly distort. Those P and B sounds that are really loud, they can cause the microphone to distort. So to avoid that, move the microphone further away, maybe use a pop filter to try to avoid those kind of loud impulses of sounds. As we get to the microphone preamp, we were very careful to avoid that red range, right? And we had this term called clipping. And clipping is a type of distortion. We reached the digital max, and clipping typically is referred to a digital type of distortion, which is usually considered kind of the worst kind. It's just so aggressive, and it's just an ugly sound. We really try to avoid it at all costs. Rarely is clipping distortion a very musical thing that we want to employ. So we want to avoid distortion in every one of those places, and you have to be very careful. And when you're recording, you're going to think of the entire signal flow and all the places that you can add level, and then after that, where you might cause distortion. And I would suggest next time you record, really think, okay, I'm going through this microphone. When can that possibly distort? At what volume would it distort? Okay, the mic pre, how do I set that to avoid distortion? And all the way through your signal flow. And then even in the DAW. Now, when you're in the DAW, there's honestly less chance of distortion. You've already converted the signal to ones and zeros, and you have much more latitude with that. But you still have to be careful. And I would still advise, mixing in a way that nothing touches the red. Nothing gets into that red. And you'll find in the DAW there'll be clipping indicators, these kind of red lights that pop on if you go above that kind of digital maximum. And you want to avoid those, again, kind of at all costs. So there are musical uses for distortion, and there are times we want to avoid it. You just want to be very aware of it. Distortion is related to the signal itself. As you get louder, the timbre of the sound is going to change, and we'll see that in more detail in the screen movie that's going to follow this. Avoid it when you don't want it, and when you are going to use it musically.
We're now going to do a short experiment to see how distortion changes wave shape in an oscilloscope and also introduces upper partials in the spectrum analyzer and the sonogram display. Remember, distortion turns volume variations into timbre variations. As I increase the level to the input of a distortion stage, which is what I'm doing here, the output is going to get brighter and brighter as we push past that distortion threshold. In this experiment, I've kept the distortion threshold right about at this line in the oscilloscope display. So when the sine wave gets up to that point, the top will be clipped off and distorted. It's very similar to a digital clipping distortion you would find at an analog to digital conversion step. Another important part of this experiment is showing the level meter. When we look at this level meter, there's going to be a background level, which is the peak level. That's what you would see in a DAW mixing board fader level meter, and also 4 triangles, which are showing us the RMS, or root mean squared. It's kind of an averaged level, and it's much better representative of how humans perceive loudness. So let's try this. I'm going to play a sine wave, and a sine wave is a very special type of wave in that it's kind of the smoothest, simplest of waves. It's energy at a single frequency. And then I'm going to increase that until it starts distorting, and we'll see how it changes on all of these displays. Here we go. As I increase the level, we're staying within the linear phase, so this is undistorted. I'm just increasing amplitude. As I increase here, we see that input is equal to output, just at a different level. As I go beyond this, we're about to start distorting. And as I increase level into this distortion stage, we see that we're introducing upper partials, we're changing the wave shape as it gets more and more distorted, and the apparent loudness is increasing drastically. Notice that the peak level has not changed, so in your DAW meter you won't see a change, but the perceived loudness changes drastically. The RMS level changes quite a bit. So we see some major changes as we cross that distortion threshold. It's important that you get to know the sound of distortion. We see that when we distort something, we change the wave shape, which we see in the oscilloscope display, and the more and more we distort something, the more upper partials are added to the sound. It will get brighter, and the apparent loudness will increase. Once we hit that distortion threshold with a clipping distortion, the peak level remains basically the same, but the RMS, or average level, which is much better representative of how we actually perceive loudness, will increase dramatically. As you can imagine, all of this has a major impact on the music production process.